So I want to talk about information bit error rate for the Hamming code that we discussed. So the aim of this note is to show the following four, at least. I want to show what a channel code is. Second item, channel introduces errors, error rate P, and this error rate can be improved with a code. So this is called a coding gain. So there is a coding benefit. So if you use bits that are related with each other, with this relation, the decoder can clean up some errors, and the error rate can be improved. And what this example does not show is the coding gain can get greater and greater as the length of the code increases. But this will give you a sense of possibilities. As the length of the channel code gets longer, the coding benefit will be greater and approaches the channel capacity. So this one will be given in the proof of a channel coding theorem. So, but at least with this note, with the calculation of bit error rate, we get the sense of possibilities. Okay. So here is the table that you guys have generated, which is called the standard array. And this is the Hamming code standard array, 7-4 Hamming code. The following table is obtained by the student Kim Yang-hyun. So I just took the liberty to take his solution as an example for my discussion here. Okay. So this standard array, if we take a look, has right here we have 16 rows. 16 rows. Okay. So here this table has 16 rows, right? And each row, I have a message bit right here, parity bit right here, and then I have from here to here 8 columns. 8 columns. So 16 is 2 to the power of 4, 8 is 2 to the power of 3. So if I multiply the 2, basically I have 2 to the power of 7 entries in this table. So from here to here, there are total of 2 to the power of 7 entries. And with the construction methods that we have taken, each entry in this table is unique. And since they are unique, and there are 2 to the power of 7, so these entries as a whole comprise the total words set. So basically, collection of these unique patterns of 7-bit binary words. So we call it words. And these 7-bit binary words are distinct with each other. And since this is a binary 7-bit binary words, there are only 2 to the power of 7 of them. Since each one is unique, that means that each word here appears in this table once, at least once, and only once. So never occur twice. If we, if we find any 2 items that are equal to each other, then we would not be able to make up the total 2 to the power of 7 binary word set, right? So this set has such a property. Each word appears once and only once. Okay, that's what it is. And when we take a look at the first column where we have a no error labeled. So this first column is the set of code words. So basically it has all 0 code word to all 1 code word. There are 16 code words. So first column is code word. Okay. And the way that we have constructed this table is based on single error patterns, right? Single bit error pattern, right? So the last bit error, second last bit error, and so on, all the way up to 7th bit error, right? So this is all possible single bit error pattern. Okay, so we add this to the code word, and we obtain these entries in the first rows. So, and then we have done the same with the second row, right? So this is the code word, and then we add a single bit error pattern, 7 of them, and we obtained the row. Okay, so this one, because of this construction method, each and every entry must be unique. Okay. All right. So that's the structure of this array. Okay. Okay. Another thing is that since each element of the row, except the first one, is a 1-bit neighborhood of the code word. Okay, so this is called hemisphere of radius 1 and smaller. So if we use geometry, so this code word, there is a code word, let's say all 0 code word, and then there is a 7 single bit neighbors. 1, 2, 3, 4, 5, 6, 7. So there are 7 neighbor of radius, distance 1. This distance is 1. So 7 neighbors with the distance 1 from this code word, which is at the center. Okay. These row elements are basically in this geometric picture. Each node right here, white node, represent each word in this row. Okay, and then there is another code word, right? Which are, for example, let's say this one, that has a 3-bit difference from the old zero code word right here. So, and then it has its own distance 1 neighbors, 7 of them, like that. So these guys are the distance 1, 1, 2, 3, 4. Yeah, yeah. These node are white circles represent the element of the of this row right here. Okay, and then from this code word and this code word, let's call it C0, and then C1, this one is C2, C0 and C2, so we can say that this is all zero code word, C0, this is C2. There is the distance of Hamming distance of 3. So there is a 3-bit difference between these two code words, okay? And basically we can do this for all the other code words, 16 of them, and each one is the center of radius 1 Hamming sphere, 16 of them, and then if we collect all of them, that will comprise the 2 to the power of 7 entries of this table. So that is the geometric structure of this of this code, of this 7/4 Hamming code. And then now imagine that there is a received word from the channel, and the channel is given like this in this equation. So received word R is a 1 by 7 binary vector. C is a code word, and E is a error pattern representing the channel error. And then basically you will receive R at the receiver. Then you want to correct the answer. You want to correct the errors, right? So how do you know that error has occurred? Basically, R is the set of all possible received words, and this one is nothing but 0, 1 word with length 7. So R is an element in this space. So R is one of these 2 to the power of 7 entries. Okay. So once you obtain that one, for example, let's suppose that maybe I need to erase this. So suppose that this R, the word that you obtained from the channel, was this one right here. Then what would you, how would you design your decoder for this event? Obviously, you will decode this R to the center of the sphere, which is the code word, which is this one. So any one of these entries occur as the output of the channel, you would decode it to the center of the Hamming sphere, which is the code word, this one. Why? Because these two has the minimum Hamming distance, okay? Compared to any other code word, you can compare, right? You can compare with any other code word. This one will have only single bit difference to this code word. So that means, the probability of such occurrence is the largest. So that is going to be the maximum likelihood decision if you design your decoder this way. All right. So basically, this table shows decision rule as well. So, you know, if another example, if you take, so let's say if this one was the received word, then you will decode it to this one, this code word. And if it was this one, then you will decode it to this one, okay? And so on and so on. So that's going to be the decoding rule, which is natural. It seems okay to us, right? The intuition tells us that that is logical. Okay, so here is the channel model. Let the channel model be given by R is equal to C plus E, and then this is element-wise modular. So if C was this, the second word, second code word, which is this one right here, and if the error pattern was this, then receive the word this. Okay. Okay. That was the table shows a number of useful insights. All possible received words are up here once and only once in the table. And all 16 code words are located at the far left column under the label no error. At each row, there are 8 entries. The first one is the code word of the first one is a code word, and the rest 7 are distance 1 neighbors of the code word. So each code word is the center of the hemisphere of radius 1. And so upon reception of a received word R, it will be given an entry in a row in the standard array, and then the decoder makes a decoding decision to the received word R, and this decision is seems to be you know, making sense, and we can actually show that it is a maximum likelihood decision. Okay.